Hello everyone, welcome to the course on data structures and algorithm. In this video we are going to talk about a binary search tree. We have already seen what is binary tree. So in case of binary tree, the only condition is that every node should have child which are less than or equal to 2. So maximum you can have 2 child. Either you can have 0 child or you can have 1 child, or maximum you can have 2 child. So this is the condition for binary tree. In case of binary search tree, there is one extra condition wherein in case of binary search tree, if we consider this as a vertex, this as a left and this as a right subtree, then the value of left subtree should be less than the value of vertex, and the value of vertex should be less than the value of right subtree. So this is an extra condition for binary search tree. So now there will be two conditions. One is number of child should be maximum 2, either 0, 1, 2, or second is the left should always be less than vertex. For example, if I am having 10 over here, so this should be less than 10, means it can be 5, and this can be more than 10, means this can be 15. So yes, this is binary search tree. It is satisfying both the condition. First about the number of child, and second is about the left, that is 5 is less than 10 is less than 15. So now with this one, let us move forward. So left subtree should contain values less than the vertex, and right subtree should contain the value greater than the vertex. Now let us try to create a binary subtree with those two conditions. We are given a sample data set. For example, let us start with this number 12. So 12 we are going to make it as vertex. Then we have 7. As 7 is less than 12, it should go on the left hand side, because we know that the left hand side value should be less than the vertex. Then next is 9. Always you start comparing from the vertex. So 9 is less than 12, so it should go on the left hand side. On the left hand side we already have 7, so 9 is greater than 7, so it should go on the right hand side of 7. Then comes 18. So again let's start comparing from 12. So 18 is greater than 12, so it should go on the right hand side of 12. Then comes 14. So again let us start comparing from root, that is 12. So 14 is greater than 12, so it should go on the right hand side. On the right hand side we are already having 18, so compare 14 with 18. So 14 is less than 18, so it should go on the left hand side. Next comes 1. So let us start comparing with the root 12. So 1 is less than 12, so it should go on the left hand side. Compare 1 with 7. So 1 is also less than 7, so it should go on the left hand side. Then comes 45. So start comparing from 12. So 12 is less than 45, so 45 should go on the right hand side. On the right hand side I am having 18, so 45 is greater than 18, so it should go on the right side of 18. Next comes 89. So 89 is greater than 12, so it should go on the right hand side of this. So that I am having 18, so let us compare 89 with 18. So 89 is greater than 18, so it should go on the right hand side. And 89 compare with 45, and 89 is also greater than 45, so it should go on the right hand side of 45. Next comes 100. So let's start comparing from 12. So 100 is greater than 12, go right. 100 is greater than 18, go right. 100 is greater than 45, go right. 100 is greater than 89, so go right. So I'll be having 100 over here. Next comes 36. So let us compare this with 36. So 12 and 36. So 36 is greater than 12, so go right. Then compare 36 with 18. So 36 is greater than 18, so go right. Compare 36 with 45, but 36 is not greater than 45, it is less than 45, so it should go left. And last is 59. So start comparing from root. 59 is greater than 12, so go right. 59 is greater than 18, so go right. 59 is greater than 45, so go right, and 59 is less than 89, so you should go left. So this is my complete binary search tree, wherein you can compare that all the elements which are, the left hand side elements are lesser than the root value, and the right hand side elements are greater than the root value. So just compare all this value over here, 1, 7 and 9. You can see that they are all less than 12. Alright, this is my left side, this is my vertex, and all this on the right hand side. So you can see that all 14, 18, 45, 36, 89, 59, 100 all are greater than 12. Or you can take any subtree also. If we take this particular subtree, then also you can see that this one is root 45, this one is 36 left hand side, and this one is right hand side. So anything which is in the left hand side of 45 is less than 45, and anything which is on the right hand side of 45 is greater than 45. So now this has been tested, and of course at the same time all the numbers are having, all nodes are having maximum 2 children. That's it. So now if I erase everything, you can see this is my complete binary search tree. Now if I move next, how can I delete something from binary search tree? Like if the tree is already given, then how can I delete? So there are 3 different cases. If the node you wish to delete, it has no child, 0 child. So what should you do? So that is number 1. So number 2, if the node that you wish to delete has 1 child, and number 2, the node you wish to delete has 2 children. So these are the 3 cases that we are going to see one by one. So let us take the very first case. So first case is the node to be deleted has 0 child. So in this case, for example, if we take the previous binary search tree that we have already created, then all these blue mark nodes are having 0 child, because the left and right both are null. So these are leaf node and they don't have any child. So if you wish to delete any one of these, then in that case the deletion is a very simple process. All you need to do is just the delete node and set the link to null. For example, I wish to delete this 1. So in that case, what are we going to do? Rather than the left pointer of 7, we will set it to null, and then we will free this memory. If I wish to, let's say, delete this 100, in that case the right pointer of 89 will set it to null, and then we'll free this 100. And likewise you can do it for anyone. For this one, if you wish to delete 36, the left pointer of 45 will set it null, and then will free this memory of 36. So this is the first case wherein you can delete a node with 0 child. Now second case is the node that you wish to delete has 1 child. So what to do? For example, in this one you can see that there is only one node. There is only one node over here which has 1 child. Except, see, if we take some other node, for example this 12 has 2 children, 18 has 2 children, 45 has 2 children, 89 has 2 children, and all others are having 0 child. So but this node number 9 is something wherein you have only 1 child. So what if you wish to delete 9? So in that case you can easily see that this pointer should be pointing to this one. If I consider this as a grandchild, and if I consider this 9 as a parent node, and this one is grandparent. So in this case, what do we want to delete? We want to delete the parent node. So in that case, the grandparent will directly be pointing to grandchild, alright, and then we will be freeing this memory. So its successor, left or right, in this case you can see it's right hand side, it is to be connected with the parent node. So 9's successor is 10 and 9's parent is 7. So the 7 is to be connected with 10. So the successor of the node, that is 10, in this case 10 is to be connected with its parent. Parent is 7. So 7 and 10 if you connect, then automatically 9 will be out of this tree, and then you can always free the memory. So this is the second case where you wish to delete a node having just one child. And the last case is, so after deletion this 7 will be pointing to 10. Last case is the node you wish to delete has 2 children. So in this case you have two options. Either you can replace by its in-order predecessor, or you can replace by its in-order successor. Let us take a simple example. For example, I am having a 10 over here, then I am having a less number on the left hand side 5, and then I am having, let's say, 1 over here, and I am having 6 over here. Then on the right hand side I am having 20, on the left hand side of 20 I am having 15, and on the right hand side of 20 I am having, let's say, 30. Now in this case, supposing if I wish to delete this 10, now you can see that 10 is having two children, 5 and 20. So the method is, first we will find out the in-order traversal. So let us see the in-order traversal. In-order traversal, we have already created a video on traversal. So if you have not referred that video, I would recommend you to refer it. And in case of in-order traversal, we keep vertex in between, and we keep right on the right hand side and left on the left hand side. So LVR. So L is this particular part. If we consider this is left part, this is right part, and this one is my vertex. So in left also I am having LVR. So you can see 1 5 6 1 5 6. Then after L is over, then go to vertex 10 10, and then let us come down again over here on the right hand side, and again LVR. So it's 15 20 30. So 15 20 30. So if you carefully look at it, this is nothing but a sorted list, because if we do the in-order traversal of any binary search tree, you are going to get a sorted list. So now let us try to remove this 10. So who is the successor and predecessor of 10? So predecessor is 6 and successor is 15. So now you have two options. Either you can replace this 10 by 6, or you can replace this 10 by 15. So if you replace 10 by 6, it would look something like this. In this case, I will be replacing this 6, removing this 6, and then I will be writing this 6 over here. So now this one is 6, and now you can see that, let me erase this part. So this part is erased. So this will look something like this. So this is one option, and you can see that 10 has been removed, but at the same time the tree is binary search tree. It has been maintained. And second option is, let me go back and do the thing again. So in second option is, let me put this 6 back over here, let me put that 10 back over there. So rather than this 6, let me put my 10 back, and then try to replace by in-order successor. In-order successor is 15. Okay, so in this case what we'll do, we'll remove this 10, we'll replace this 10 by 15. So I'll be putting 15 over here, and once that 15 is put, what I'll do, I'll now remove this 15. So in this case also you can check that the left hand side of 15 is all the number which are less than 15, and the right hand side of 15 is all the number which are greater than 15. So these are two different ways to do this. So now let us take another example, the same example that we had. So if we wish to delete, let's say 12. So in case of 12, if you put everything in sequence, then it will be like 1, then 7, then 9, then 10, then 12. This is in order traversal. Then again 14, 18. So 14, 18, then 36, 45, then 59, 89 and 100. So this is Inorder traversal, and what I want to delete is 12. So now there are two options. If you can see, there are two options. Either you can have the left hand side, that is Inorder predecessor, or you can replace 12 by Inorder successor, 14. So you can do these two different things. Either you can replace this 12 by this 10, or you can replace the 12 by this 14. So now let us see this. So first thing is, now I have replaced it by 10. So this 10 is gone from this place, and I have replaced 10 in place of 12. Or other option is, let us keep 10 as it is, and use this 14. So 14 is gone from this place, and I have put the 14 over here. In this case, the 10 is gone from over here, I have put it over here, 10. So these are the two different ways to do deletion from binary tree for the node having two children. Now if you wish to construct a binary search tree from pre-order data, for example, a pre-order data is already given, and pre-order is the vertex comes first, then left and right. So this 50 is nothing but my vertex. Now you wish to construct this pre-order data. So for that, first we will be converting this into Inorder, and Inorder is nothing but the sorted list. So if I sort this 20, then 30, then 40, then 50, so likewise this will be my Inorder data. So you need to have Inorder data also. So let us first try to do this. So our root is 50 because V comes first. So V is vertex, vertex is root. So the root is 50. So first we will be putting 50, and then if you see in this particular sorted order, we have something in the left and something in the right. So something in the left, 20, 30, 40 should go on the left hand side over here, and something in the right should go on the right hand side of 50. Now out of this 20, 30, 40, which one should be made as root? So for that, now you will be scanning through this. Now 50 has already been scanned and it has been put over here. So next comes 30, because now vertex should come first in this sorted order. So next comes 30. So you will be making 30 as vertex, and because 20 is less than 30, it should go left. 40 is greater than 30, so it should go right. So out of this 20, 30, 40, the 20, the very next element, should become the root for that particular subtree. So now you can see it goes something like this. Now for this 60, 70, 80, 90, which one should be made the root? So for that also you will be scanning like this only, and now you can see this somewhere over here you have found 60. So we will be making 60, and if you check this out, 60, all the numbers 70, 80, 90 are on the right hand side. So now I'll be putting 70, 80, 90 on the right hand side. Now out of this 70, 80, 19, which one should be made root? So for that again I'll be checking, and I can see that I found 80 first. So I'll be making 80 root, and 70 goes on the 80 root, and 70 goes on the left hand side, and 90 goes on the right hand side. So 70 goes on the left hand side and 90 goes on the right hand side. So this is my complete construction of binary search tree from a pre-order data given. So if a pre-order data is given, you can construct a binary search tree like this. And if post-order data is given, for example in this case the vertex is at the end, the LRV, the vertex is at the end. So in this one also we will be first creating Inorder traversal, and Inorder traversal is nothing but simple sorting of these nodes. So 20, 30, 40, 50, 60, 70, 80, 90. So again we start with the same thing. 50 we make root, the last node. In pre-order we took the first node, in post-order we take the last node. So last node we take as 50, and then in order you can see that there is something in the left hand side that I'll be putting here, and there is something on the right hand side that I'll be putting here. Now for the left hand side, I am having 20, 30 and 40. So now I will scan from this place. So in this one 20, 30 and 40, you can see that 30 comes first. 30 comes first if I scan from left to right, because in post order we scan from right to left. In earlier case we scan from left to right. So we scan from right side and we go all the way up to left, and we see that 30 comes first. So I'll be making 30 a root, and then for 30 something is on the left, something is on the right. So 20 is on the left and 20 is on the right. Now if I take this one 60, 70, 80, 90, so if I scan from this one, you can see the 60 comes first, so it will be 60. And if I see in this in order, there is nothing on the left but everything is on the right, 70, 80, 90. So I'll be putting 70, 80, 90. And now with this 70, 80, 90, which one should come first? So for that also you will be scanning this one. So 70, 80, 90, you can see 80 comes first. So 80 should be your root, and if you consider 80 as a root, 70 is on the left hand side, 90 is on the right hand side. So 70 is on the left hand side, 90 is on the right hand side. So this is how you can construct a binary search tree from a post order data. And now binary search tree from, now let us see how to construct a binary tree from a general tree. General tree is something wherein the number of child are not restricted. So in case of general tree, I can have any node can have 1, 2, 3, 4, any number of child. So let us take one example. This is a general tree, and we can see that A is having 3 children. That means in case of binary tree you can have maximum 2 children, but in case of general tree there is no restriction. So in case of C over here we are having 3 children, and likewise. Now how to convert this general tree into binary tree? So there are 3 basic rules to convert. The first one is the root or node of general tree would become the root node for the binary tree. So this is the first condition. So this root will become the root for the binary tree. So that A will become the root for binary tree. Now second is leftmost child of any node in general tree would become the left child in binary tree for that particular node. For example, A is having 3 children, but which is the leftmost child? B. So in the binary tree, B will be the left child for A. And the third simple rule is the next or right sibling of any node will become the right child for that particular node in binary tree. We can see that B, C and D are siblings. Siblings are the node for which the parent is common. For example, F, G, H. So F, G and H are the nodes for which the common parent is C. So the next node for B is C. So in the binary tree, C will go on the right hand side. The next node of C is D. So in the binary tree, the D will go on the right hand side of C. Now let us see how to construct the binary tree from this general tree. So first let us put A as a root. Now out of this B, C and D, which one is the leftmost node? The leftmost node is B. So I am going to put B as a left child of A. Then again I am having the leftmost or the left child of B as E. So I am going to put that over here as E. Now what about the right child? Because E does not have any more left or right, so this is done. What about the right child of B? So we know the next right sibling of B becomes the right child of B. So over here it is C. So C becomes the right child of B. Now C is having 3 children, F, G, H. Which is the leftmost children? The leftmost children is F. So the F will become the left child for C. Now for F, the right child will be the next sibling, and next sibling is G. So right child of F will become G. and the right child for G will be H. So right child for G will be H. Now if I come back to this C, the next sibling would be D. So D will be the right child for C. Now D is having 2 children, and out of them this one is leftmost. That means I is leftmost. So that will become the left child of D. And over here the sibling of I is J. So that will become the right child of J. And J is having only one children which is on the left hand side. So J will be having one children which is on the left hand side. So now using this we have created a binary tree. And what is the condition of binary tree? The number of child should be not greater than, the number of child should be either 0, 1 or 2. It cannot be greater than 2. So you can see this: for A the number of child equal to 1, for B it is 2, for E there is no child, for C there are 2 child, for F 1 child, for D 1 child. So 1, 1, this 0, 1 and 0. So it lies in this range 0, 1, 2. So this is my binary tree. So if I draw this whole thing again, so you can see from A, then left B, then left C. So this part is done. Now the right part of B is C, then for left part of C is F, then right to F is G, then right to G is H, then now come back to right to C. Right to C is D, then the left part is I, then right of I is J, and left of J is K. So this is how we construct a general binary tree. And with this we conclude this video, and in our next video we will be talking of AVL tree. So thank you guys for being here.